Hello students, I Neha Yadav, Assistant Professor in ABS Engineering College, Ghaziabad. Today I am going to teach third topic of Unit 4 of Discrete Structure and Theory of Logic. The topic is Group and Abelian Group. So what is a group? A group is an algebraic structure which follows the following four properties. The first property is the closure property. So closure property says that, for example, if this is an algebraic structure, so it should satisfy the closure property. In algebraic structure, G is a non-empty set and this is a binary operator. So closure property states that if we apply this binary operator between any two elements of this group, the result should belong to this particular set only. If the result belong to this particular set, then we will say closure property is satisfied. Second property is associative property. So what is associative property? For example, if we are considering a set of integer, for example, the group given is set of integer with binary operator addition. So if we check whether the associative property, if we want to check whether the associative property is satisfied or not, then we should consider any three integers and we will apply the addition operator over these three integers, and we will check whether after changing the association of addition between these three integer value, we are getting the same result or not. First I have taken 1 and 2 together and then I am adding 3 in the result of addition of 2 and 1, and if I add 1 to the result of 2 and 3, we will get a same result, which is 6. So here 6 is 6. So in this case, for integer with addition, associative property is satisfied. So any algebraic structure in which associative property is satisfied is known as semigroup. The third property for a algebraic structure to be a group is existence of identity element. So we have to find in the given set or in a given algebraic structure, first we have to find the identity element. The method to find the identity element is explained in detail in previous lectures of this unit. Here I will give an example. If we have a set of integer and we have to find the identity element for this particular group, then we can take, for example, any one integer. For example, it is 2. So for when we apply addition operator to this particular integer, then what should I add to this particular value, this particular integer, so that we can get the same value as a result. The integer which we are considering is is came as the output of this particular value. So what should I add to 2 to get the output as 2? So it is obviously 0. If we consider any other integer, for example, what should I add to 3 so that I can get output 3? So here it is also 0. So for this set, for set of integer with addition, I am getting identity element as 0. So identity element is mostly connected to the operator. If the operator is add, we can consider any element with, suppose it is A. It can be any element. If we add something to this element and we want a result as that element only, we should add 0 only. So for addition, the identity element is always 0. Now we have to check whether this identity element is existing in the set given in the group or not. If that identity element is existing in the set, then we can say that the third property is also satisfied, that is identity element is existence, or we can say that yes, existence of identity element is satisfied. The last property is inverse. So for inverse, we can check find the inverse of each element of the set. So here, as the set is infinite set of integer is an infinite set, it is not possible to find the inverse of each set, but we can find the inverse of one or two elements so that we can get a pattern what will be the inverse of a integer when we check when we go for checking whether it is a group or not. For example, consider one integer, let it be 3. So what should I add to 3? Why addition? Because here the operator given is addition. What should I add to 3? I get identity element, and for addition we know that identity element is 0. So what should I add to 3 so that we can get a 0? We all know that it is -3. So for all integers, for z, minus z is always the inverse of it. For any element a, b belongs to z, its inverse will always be minus a minus v. So here for all these set of integers, for all integers, its inverse will exist, as the negative of a integer is also a integer. So negative inverse of the each integer is also coming in this group only. So here inverse property should also satisfied. So for, if I summarize this, for an algebraic structure to be a group, four properties must satisfy. The first property is closure property, second property is associative property, third property is existence of identity element, and the last one is existence of inverse of each element of that particular group. If these four properties satisfied, then that algebraic structure is known as a group. Now comes the abelian group. What is an abelian group? So abelian group is also a group which satisfies commutative property. So if we summarize it, for a algebraic structure to be a group, there should be four properties should satisfy. The first one is closure, the second one is associative, the third one is existence of identity element, fourth one is existence of inverse element. For a group to be abelian group, one more property should satisfy in addition to these four properties. So the last properties is commutative property. Commutative property is simple property which says that if A operation B is same as B operation A, we can say that commutative property is satisfied. So now we will consider some examples which are based on group and abelian group. The first example is show that the set of all integers is a group with respect to addition. So here the question is set of, as I discussed previously also, set of integer. We have to show that whether it is a group or not. So we know that for a group, it should first be an algebraic structure. And for algebraic structure, so for algebraic structure, it should satisfy the closure property. And closure property says that if we take any integer, any two integer out of these integers and apply the addition operator between these two integer, the result which we will get should belongs to this particular set, the set of integer. And we know that if we add any two integer, whatever it may be, for 1000 plus 2, it will always be an integer only. So we can say that if we apply this operation between any two integer, we will get a integer value only. So closure property here satisfied. Second is, as closure property is satisfied, this is a algebraic structure. Second is semigroup. What is a semigroup? A semigroup is a algebraic structure where associative property is satisfied. So here we will check for associative property. So here I am considering any three element out of this set. It may be A plus, we will apply the operation given in this group, addition operation, B plus C. And for checking whether associative property is satisfied, we have to change the association and check whether the result will affect or not. Here for addition, it is the result is not based on the association. For example, if we take some value of A, B, C, for example, A is 1, B is 2, and C is 3. Here A is 1, B is 2, C is 3. Here we are taking this association, and here I change the association. Whatever be the association, in case of addition, we will get the same result only. So here for addition, if the operator is addition, the associative property will always satisfy. So if this associative property is satisfied, this means it is a semigroup. So two properties are satisfied for set of integer with addition. The third property is existence of identity element. And as previously discussed, identity element in case of addition is always 0, and we know that 0 is an integer. So 0, this identity element exists in this group. So third property is also satisfied, and this is also a monoid. Fourth property is existence of inverse of each element. As this is the infinite set, so it is not possible to find the inverse of each element of this infinite set. So we will find a pattern whether the inverse of integers with addition will exist or not. Let me take an example. Let me consider a integer 2, and if we do addition with what, so that I get identity element, it is always -2. So -2 is the inverse of 2. I can take any other example, 100. What should I add to 100 so that I can get identity element? It is always -100. This -2, -100, these all are integers. So if we take any integer, if this is integer, then minus a, minus b, minus c will always be integer, and these are the inverse of these values. So here we can see that inverse of all the integer is also a integer. So inverse also exists in this particular group of integers. So here we can say that the fourth property is also satisfied. As all the four properties are satisfied, so this is a group. A set of integer with addition is a group. Here is the next example. Show that all set of show that set of all non-real numbers, set of all non-zero real number is a group with respect to multiplication. So here a set of real number except zero, non-zero real number is given, and the operation is multiplication. So similarly, as in the last case, I will check for closure property. If closure property will satisfy, it will be a algebraic structure. Then I will check for associative property. If associative property will be satisfied, then it will be a semi group. And then I will check for identity. If identity element will exist, then it will be a monoid, and then I will go for inverse. I will check for inverse. If there exists an inverse of each element of this set, then it will be a group. So set of real number with multiplication. Set of real numbers are all the numbers with with or without decimal value. So if we apply multiplication between any real numbers, any two real number, for example, 1.5 into 2. So it is always 3. So 3 is also a real number. If we take some other example, for example, it is 3 into 2. 3 and 2 both are real. 6. 6 is also a real number. If we apply multiplication between any two real number except 0, we will get a real number only. So closure property is satisfied. Now check for associative property. Here operation is multiplication, and we know that multiplication always supports associative property. If we change the association, the result will not change. So consider any three real numbers, take it as 1, 2, 3. If we change the association, it will not change our result. The result will always be 6 is equal to 6. So associative property will also hold for this case. Now identity element. We know that, as explained in the previous lecture, we know that for multiplication, identity element is always 1. And now we will check for inverse of each element of this set. So how to find the inverse of an element? Consider any element, any real number. For example, it may be 6. If we multiply, what should I multiply with 6 to get the identity element? For example, it is, let's suppose take it A inverse. ठीक है, it can be, so A inverse will be 1/6. 1/6 is a real number. 1/6 is always a real number. So whenever we find that, we can take any real number, we will always get a number here which is always a real number. So inverse of each real number except 0, if we take 0, if we consider 0, what should I multiply to 0 so that I can get identity element? There is no number, so inverse of 0 does not exist. Clear? If this is not given in the question, non-zero is not given in the question, then this is not a group. But as it is mentioned in the question, we are considering only non-zero real numbers, so all properties are satisfied. The last property, inverse property, is satisfied for every element except 0, and in question it is given that non-zero real numbers are considered. So this, the real number without 0 is always a group. If we consider another question where we will take real number with multiplication, and here we are taking 0, we are also adding 0 to it, then it will not be a group. Next is an example of abelian group. Here is a set given which says that which has element 1, -1, I, this is I, small I, and with multiplication. So the group here is 1, -1, I, and -I. This is the set, and the operator is multiplication. So here we have to check, I have to check that whether this is an abelian group or not. So as we know that for abelian group, 5 properties should satisfy. The first one is closure. So here the set is finite set. So here we can check the closure property using composition table or Kelly's table, or we can also say call it as the closure table. So we will perform the multiplication between all of the two pairs or two combination out of this particular set. So 1 into 1 is 1, 1 into -1 is -1, 1 into I is I, 1 into -I is always -I. -1 into 1 is -1, -1 into -1 is 1, -1 into I is -I, -1 into -I is I into 1 is I into -1 is I into I is I square. I here is a complex number, and we know that the value of I square is always -1. So here it is -1. I into -I is -I square. -I square will give us 1. -I into 1 is -I. -I into -1 is I. -I into I. -I into I. So it will again be 1. -I into -I will be -I. -I into -I. Minus will become plus, and it will be I square. So it will be -1. So here we can check that if we perform multiplication between any two number of this set, we are getting, as a result, we are getting all the elements which are in this set only. So here we can see that closure property is satisfied. So it is an algebraic structure. The second property is associative property. Associative property, as we know that multiplication is always support associative property. 1 into -1 into I, whether it be this association or it be this association, it will always give us -I on both sides. So here associative property is also satisfied. So closure satisfied, associative satisfied. The third property is existence of identity element, and we know that in case of multiplication the identity element is always 1, and here we can see that 1 belongs to this particular set, so our identity element is also existing, hence the third property is also satisfied. The fourth property is inverse of each element. Here we will calculate the inverse of each element. We can calculate here also, or we can directly calculated from the closure table. How inverse is find? what should I, if I am going to find the inverse of 1, then the definition says that what should I multiply to 1 so that I will get a identity element. Identity element here is 1. So I should multiply 1 to 1 to get identity element as 1. So inverse of 1 is 1. What is inverse of minus 1? What should I multiply with minus 1 so that I get identity element? So inverse of minus 1 is minus 1. What is inverse of I? What should I multiply to I so that I get 1 or identity element? It is minus I. So inverse of I is minus I. Similarly, inverse of minus I is I. So here 1, minus 1, I and minus I all belongs to this particular set. So I will say that inverse of all these element is exist. So the fourth property which is necessary for an algebraic structure to be a group is also satisfied. So here this structure, this group is an this structure is a group. Now I will check for the fifth property which is necessary to prove a group to be a abelian group. The last property is commutative property. So I can check by taking any two element of this set, the commutative property. 1 into minus 1 is always equal to minus 1 into 1, or 1 into I is always equal to I into 1. So multiplication operation always supports commutative property. So this group is also the fifth property. Commutative property is also okay. So this group is also an abelian group. Here is another example for abelian group. The set here is, this example is bit different from the last example. Here the set given is set of integer and the operator here is star, and in the question the definition of this operator is given in the question. This is an equative question. The definition says the operator star says if we apply this star operator between any two values, then what will it give? A plus b minus 2. So now we have to prove this as the abelian group. So the first property we have to prove is closure. So consider any two element, for example 2 star 3. So 2 star 3, if we apply this particular operation using this definition, it will always give you 3. I am getting 3. Consider any other two integer, any integer, any two integer. 5 into 5 star 10. 5 star 10 will give you 5 plus 10 minus 2. So it will be 5 plus 10, 15 minus 2 is 13. If we take any integer, I will always get a integer. This is an integer, this is an integer. I will always get a integer as a result, which is the set given. So closure property will always satisfy in this case. The second property is associative property. Consider any three integers, 1, 2, 3. So if I perform star operation between any three integers, 1 into 2 into 3. So 1 into 2, as per the operation given, 1 star 2 is 1 plus 2 minus 2. Here 2 star 3 is 2 plus 3 minus 2. So here it is 1 star 3, and here 1 star, here 2 and 2 will get cancelled, 1 star 3. So these are equal. We are getting equal values, so associative property is satisfied. Third property is identity. So here we have to calculate the identity element, as here the operation is not the common operation like addition or multiplication. So we know the method to calculate the identity element. Consider any element from this set, let it be 6. We perform the operation star with what value, so that we will get again this element only as a result of the operation. So let's check. Consider it as P. So if we apply star between 6 and P, we will get result 6 plus P minus 2 is equal to 6. So P will be 2. If we take any other, if we calculate identity element considering any other integer in place of 6, then also we will get identity element as 2 only, and we know that 2 is also a integer. So identity element also exists in this particular set. So here it is also a monoid. Then the fourth property is inverse. We will calculate inverse. So the method to calculate inverse is consider any integer, let it be 3. We will apply the operator. Here is the inverse. Consider it as I, and we will get the identity element. So here, open the equation, is equal to 2, I is equal to 4 minus 3, I is equal to 1. So inverse of 3 is 1. So 1 is also an integer. Calculate inverse of any other integer. We will always get a integer value as the inverse of any of the integer. So here the inverse property is also satisfied. The fifth property is commutative. Commutative property is if we perform A into B, A star B, it should be equal to B star A. So check whether this property is satisfied or not. Consider any two integer. For example, 1 into 2. So if we are taking 1 into 2 or 2 cross 2 star 1, we will always get the same value, 1 plus 2 minus 2. So we will get 1 on both sides. We will get 1 is equal to 1. So last or and fifth property is also satisfied. So this is an abelian group. This is a reference textbook for discrete mathematics. Thank you for patience listening. Thank you so much.